Hi everyone. In this video, we will discuss the water treatment and technology. At the end of this session, students are able to understand the history of water treatment, identify the water quality categories, understand the different treatment systems, calculate problems related to coagulation, flocculation, mixing, and sedimentation, and explain and calculate problems related to filtration and disinfection. So when we say of water treatment, it has a lot of issues. And one of these scenario is in the town in Walkerton, Ontario. So people living in the town were served by several wells drilled 15 to 76 meters deep. And they found out that residents become ill, so the Utilities Commission began sampling the wells and confirmed that it was contaminated by a microorganism commonly known as the E. coli. As a result, two patients died and 500 residents complained of the symptoms. They found out that the culprit was the E. coli 0157H7, or commonly known as the Campylobacter jejuni. That is why nowadays, water treatment is very important, especially to the community. To begin with, let us discuss the history of water treatment. As early as 4000 BCE, or before the Common Era, the Greeks and southeastern Indians recognized the importance of water treatment for controlling taste and odor. So they used filtration of water through charcoal, irrigation by sunlight, and boiling, which are mentioned in ancient Greek and Sanskrit documents. So as early as 1500 BCE, the ancient Egyptians used alum to clarify the water. And in 1685, the Italian physician Lucas Antonius Porcius described a multiple sand filtration method involving three pairs of sand filters. In 1703, the French scientist La Hire offered a proposal to the French Academy of Sciences suggesting that every household should have a sand filter to treat rainwater. And in 1908, chlorine was first used in the United States to disinfect drinking water. In New Jersey, resulted in a significant decrease in the number of deaths due to typhoid. So since ancient times, people have realized the importance of water. So they use it for navigation, drinking, recreation, and in religious rituals. However, most of the emphasis has been on the quantity rather than quality. So where consideration of the quality does occur, these discussions have pertained mainly to the aesthetic properties of water. Now let's move on to water quality. As consumers, we expect our water to be both aesthetically pleasing and safe to drink. Water that does not impart a taste or odor and is therefore pleasant to drink is called palatable. Water that is free of chemicals, microorganisms, and other contaminants, and is therefore safe to drink is called potable. So the following three categories are used to describe drinking water quality: the physical characteristics, chemical characteristics, and microbiological characteristics. First, let us discuss the physical characteristics. Water suppliers monitor such physical characteristics as turbidity, color, taste, and odor and temperature. Turbidity is caused by the presence of the suspended material such as clay, silt, finely divided organic material, plankton, and other particulate material in water. So although turbidity may not adversely affect health, these particles may harbor microbiological contaminants that are harmful to human health or that decrease the effectiveness of disinfectants. Dissolved organic material from decaying vegetation and certain inorganic matter may cause color in water. So the excessive blooms of algae or the growth of aquatic microorganisms may also impart the color. Although color itself is not usually objectionable from the standpoint of health, its presence is aesthetically displeasing and suggests that the water needs appropriate treatment. Color can also be caused by the inorganic metals such as iron or manganese or by humic substances which are formed from the degradation of leaves and other organic debris. The foreign matter, such as the organic compounds in organic salts or dissolved gases, may cause taste and odor in water. So certain types of the algae, especially the blue-green algae, can also impart foul taste and odor that could affect the physical characteristic. Now let's move on to the chemical characteristics. Water treatment plants monitor for a variety of inorganic and organic constituents, including chloride, fluorides, sodium, sulfate, nitrates, and more than 120 organic chemicals. However, these chemical species are viewed as contaminants because of their effect on water quality. Some of these chemicals are monitored for health reasons, others other aesthetic purposes. Like for example, iron and manganese rarely pose a health threat, whereas the presence of nitrate can cause methemoglobinemia or the blue baby syndrome in infants. Nitrates most often originate from the application of agricultural fertilizers, whereas iron and manganese are naturally occurring. Now let's move on to microbiological characteristics. Water for drinking and cooking purposes must be made free from disease-producing organisms such as viruses, bacteria, protozoa, and helminths. Unfortunately, these specific disease-producing organisms present in water are not easily identified. The techniques for comprehensive bacteriological examination are complex and time-consuming. As such, it has been necessary to develop tests that indicate the relative degree of contamination in terms of an easily defined quantity. The most common causal agent of waterborne diseases is the protozoal parasite Giardia lamblia. Some organisms that cause disease in humans originate with the fecal discharges of infected individuals. Others are contained in the fecal discharge of animals. The most widely used bacteriological assay estimates the number of microorganisms of the coliform group. These groupings includes two genera, the Escherichia coli and the Aerobacter aerogens. So the name of the group is derived from the word colon. The Escherichia coli are gram-negative bacteria that commonly inhabit the intestinal tracts of mammals, while the Aerobacter aerogens are commonly found in soil, on leaves, and on grain. On occasion, they cause urinary tract infections. The test for microorganisms, called the total coliform test, was selected for the following reasons. E. coli usually inhabits the intestinal tracts of humans and other mammals. Thus, the presence of coliforms is an indication of fecal contamination of water. Second, even in acutely ill individuals, the number of E. coli excreted in the feces outnumber the disease-producing organisms by several orders of magnitude. The large numbers of E. coli make them easier to culture than pathogenic organisms. Thus, the presence of coliforms in water implies fecal contamination rather than growth of the organism because of the favorable conditions. So these organisms also survive better in water than most of the bacterial pathogens. This means that the absence of coliforms is a reasonably safe indication that pathogens are not present. Third is that the coliform group of organisms survives in natural waters for relatively long periods but does not reproduce effectively in this environment. And the fourth is the coliform group of organisms is relatively easy to culture. Next, the water classification by source. Although salt water is occasionally used as a drinking water supply, fresh water is the preferred source. Potable water is most conveniently classified as to its source, that is groundwater or the surface water. Although in general, the deeper the well, the greater the level of protection from contamination. Deep wells only provide protection when the wells are properly designed and operated so that surface contamination is prevented. Groundwater is pumped from wells drilled into aquifers The quantity and quality of water available depends on the type of geological formation forming the aquifer and the properties of the contaminant itself. Drinking water wells can be shallow, less than 15 meters, or deep, greater than 15 meters. Surface water includes rivers, lakes, and reservoir. This is the general characteristics of groundwater and surface water. So for groundwater, we have the constant composition, whereas for the surface water, we have the varying composition. For groundwater, we have the high mineral content, and for the surface water, we have the low mineral content. In groundwater, we have low turbidity, low or no color, while in surface water, we have high turbidity and color. In groundwater may be bacteriologically safe, while in surface water, microorganisms are present. In groundwater, no dissolved oxygen. In surface water, there are dissolved oxygen. In groundwater, high hardness is present, while in surface water, low hardness is present. In groundwater, there are hydrogen sulfide, iron, and manganese, while in surface water, taste and odors are present. Both groundwater and surface water have the possible chemical toxicity. Now let's move on to the treatment systems. Water treatment facilities in developed countries are typically coagulation plants, softening plants, and limited treatment plants, whereas some countries uses the combination of coagulation, softening, and the limited treatment plants. Coagulation plants are typically used to treat surface water and remove color, turbidity, taste, and odors, and bacteria. So most plants use coagulation, flocculation followed by sedimentation, and then filtration and disinfection. However, higher quality surface waters can be treated using direct filtration, in which case sedimentation is omitted. Softening plants are typically used to treat groundwater that has a high hardness. This is the flow diagram of a conventional surface water treatment plant. As shown in the figure, the raw surface water or the surface water supply is pumped from a stream, river, lake, or a reservoir using the low lift pumps into the coagulation plant. The water is first screened to remove the large material, including twigs, the plant material, fish, and even the rocks. So during rapid mixing, chemicals called the coagulants are added and rapidly dispersed through the water. In the flocculation basin, the chemical reacts with the precipitate, and they are usually removed by gravity in the sedimentation basins. Following the sedimentation, the clarified water is distributed to rapid sand filters to remove residual turbidity. So disinfection is then used to reduce the number of pathogenic organisms to levels that will not cause disease. So it is usually achieved by the addition of chemicals such as the chlorine, chloramines, or the ozone, or the application of the UV radiation. So after disinfection, it will be stored in a storage tank or in a storage vessel for distribution system. Another flow diagram of a direct filtration plant. So from the surface water supply, the stream, river, or lake, it will undergo screening, and then the addition of the coagulant, and then the rapid mixing, the flocculation basin, rapid sand filter, disinfection, and then the storage. The sedimentation process is omitted in this flow diagram or in this process. Also another flow diagram of water softening plant. The groundwater from wells will undergo rapid mixing, and then after that it will enter the reaction basin and then the settling tank for sedimentation. So the sludge is removed. After sedimentation, it will undergo recarbonation and then rapid sand filter, disinfection, and storage for distribution system. Now let's